The Boy's First Book of Radio and Electronics, Alfred Morgan, 1964. Chapter 3, About Radio Waves. If you stand at the edge of a pond and strike the surface of the water with a stick, ripples or small waves will spread out from the spot on the surface where the stick struck. The little waves will spread in circles until they reach the opposite shore if it's not that far. It would be possible to arrange a code or signals so that by counting or timing the waves, they could carry a message to another person standing on the opposite shore of the pond. For example, two groups of waves, one following after a short interval, could mean no. In the same way, three groups of waves, spaced a few seconds apart, could signal yes. This simple arrangement, whereby groups of waves carry a message, illustrates the principle of radio communication. More than 50 years have passed since the first wireless telegraph message was sent and received, but present-day radio communication uses the same basic principles employed before the turn of the century. Broadcasting, television, radar, LORAN, radio telegraphy, and radiotelephony consist of creating and detecting Hertzian waves. The radio apparatus now in use is vastly more complicated and more efficient than the first radio apparatus, but radio still depends on the discovery that 1. When a very rapidly alternating electric current flows into an antenna wire, some of the electrical energy will radiate out into space in the form of Hertzian waves. 2. When the waves strike another antenna, they will create therein feeble alternating currents similar to those which produced the waves. A radio broadcast receiver changes these feeble currents into sounds. A television receiver changes them into sounds and pictures. Radio apparatus for producing radio waves is sometimes arranged so that the waves are formed into a beam, like a beam of a searchlight, which can be sent in any direction. The radio waves used for communication between Europe and America and between the North and South America are beamed in this manner. In the early days of wireless, the antenna was usually arranged so that the waves spread out in circles with the transmitting antenna at their center. The meaning of the word radio. The fact that electric waves are a form of radiant energy and radiate from an antenna brought a new word into use. Radio replaced the earlier term wireless and has been adopted into our language to mean the transmission and reception of signals by which of electric waves without connecting a wire. The word wireless is still in use in Great Britain. How electromagnetic waves are produced. When Hertz discovered how to produce electric waves, the waves were named Hertzian waves in his honor. This term is seldom used nowadays. The name as popular is radio waves and air waves. The term airwaves is often used by newspapers and radio announcers, but is a complete misnomer. Hertzian waves are not airwaves. They pass through air moving to or from a radio station, but the air is not the medium which makes the passage possible. The effect on the air on Hertzian waves is so slight that it can be ignored for practical purposes. Winds do not disturb the waves. Air, which is ionized, the air molecules bear an electric charge when air is ionized, has an effect upon the path of the radio waves, and as we shall see later, aids in long-distance radio communication. Hertzian waves, or radio waves as they will be referred to in the remainder of this book, are electromagnetic waves. They have both an electrical and magnetic character. Radio light, heat, X-rays, and many other effects are due to electromagnetic waves. The apparatus for creating radio waves is called a transmitter, that which detects the waves and renders their messages intelligible is the receptor, or it is popularly called the receiver. Radio waves are created by sending rapidly alternating currents into an insulated wire called an antenna. An antenna is used also at the receiver to pick up or intercept incoming waves. In this instance, insulated wire does not mean a wire covered with insulation. Antennas are usually bare wires, insulated from the earth, from their supports, and from the surrounding objects. However, there is a type of antenna which is known as a grounded antenna. It is insulated in the usual manner, except at a point where it is purposely connected to the earth. And an antenna may consist of a single wire or an elaborate arrangement of wires. These statements do not apply to all antennas used for television, radar, and the extremely short waves called microwaves. In the pioneer days of wireless telegraphy, the waves were produced by rapidly charging and discharging the antenna with high voltage currents from an induction coil. This method was soon replaced by better procedures for generating rapidly alternating currents and sending them into the antenna. Transformers connected to Leyden jars or condensers, electric arcs, and alternators were used as generators of high-frequency alternating currents for producing electric waves, but none were wholly satisfactory. Nowadays, a rapidly alternating current which is sent into the antenna are generated by electron tubes. Without such tubes, present-day wireless telephony and broadcasting and television would not have been possible. Radio waves have length and frequency. A radio broadcasting station is not permitted to operate unless it has a government license. Each license is licensed to send out waves of only certain wavelength or frequency so that it will not interfere with other radio stations whose programs are heard in the same area. The frequency of a wave is the number of waves in which occur in a second. For example, station WABC in New York City is licensed to send out a wave having a frequency of 770 kilocycles. WNBC and WOR, both also in New York City, have assigned frequencies of 660 and 710 kilocycles respectively. Kilo means 1,000. When the waves move along the surface of the ocean or a lake, the distance from the crest of one wave to the crest of the following wave is the wavelength. The distance from crest to crest of a radio wave is also a wavelength. Although radio waves are invisible, their wavelengths can be accurately measured by appropriate scientific instruments. Radio waves are always measured in meters or centimeters because scientists use the metric system of meters and centimeters in preference to the English system of feet and inches. A meter is 39.37 inches, or the equivalent of 3.28 feet. A 200-meter wave is therefore 656 feet long. There is no sharp dividing line where long radio waves cease to be long waves and become short waves. It is customary to consider short waves to be those with a wavelength of less than 200 meters. Also, radio waves are divided into the following groups: ultra-short radio waves, 10 meters and less; short waves, 10 to 34 meters; medium short waves, 34 to 200 meters; long waves, 200 to 30,000 meters. How radio waves behave. Radio waves travel through free space at the same speed as light waves, roughly 300 million meters or 186,000 miles per second. Radio waves are much longer than light waves. They range in length from approximately 30,000 meters to a fraction of a centimeter. The meter is the equivalent of 39.37 inches. A centimeter equals 0.3937 inches. The frequency of radio waves ranges from 10 kilocycles to 1,000,000 megacycles. A megacycle is 1,000,000 cycles. The shortest waves have the highest frequencies. Radio waves can be reflected and refracted like light waves. Reflected means thrown back, like sunlight thrown back in a mirror. When radio waves graze the edge of an object in passing, for example a hill, they tend to be bent around the edges of the object to a slight extent. This type of bending is called diffraction. Some large objects, such as hills or buildings, cause radio shadows to be formed. The waves do not bend enough to enter the space behind the object, so there is a radio shadow there. Another type of wave bending is called refraction. Refracted means bent. The bending known as refraction occurs when waves move obliquely into an air mass which has a different electrical qualities from the atmosphere they leave. There are changes in the electrical characteristics of the air at the boundaries between the atmospheric areas of different temperatures and moisture content. Refraction occurs at those boundaries. Reflection, refraction, and diffraction account for part of the behavior of radio waves. The reflection of radio waves makes radar possible. Smokestacks, tanks, power wires, bridges, hills, mountains, and many other objects reflect radio waves. The Germans took advantage of this fact during World War II and were the first to shower metal-impregnated paper clips over the battle area. Radio waves were reflected by the metal and confused the Allied radar warning network. Later, the Allies adopted the same trickery and showers aluminum foil to confuse the German radars and hide the position of the Allied bombers on their way to the targeted Germany. The reflection of waves, which takes place 55 to 195 miles above the surface of the Earth, has a marked effect upon radio communication. This region, high in the heavens, where the reflection and refraction of radio waves takes place, is known as the ionosphere. The length of radio waves and the type of antenna from which they radiate greatly influence the path they follow through space. When radio waves move away from the antenna of a broadcasting station, they travel through space by two routes. Some have their feet on the ground and follow the surface of the Earth. They are called ground waves. The strength of ground waves fades very rapidly as they move away from the transmitting antenna. Other waves, called sky waves, leave the Earth's surface and travel outward and upward in space. Somewhere in the upper atmosphere, they meet the region of the ionosphere that reflects and bends them so they return to Earth again. The short waves used in television do not follow the curvature of the Earth. They go forth in a horizontal line, like the light beam from a lighthouse. The path of radar waves is like the path of a light beam from a searchlight. The effect of the ionosphere is bending the radio waves so they return to Earth at distant points. How low-powered, shortwave amateur radios can communicate halfway around the world. Radio stations send further at night. It has already been explained that the ground waves quickly become weak as they travel away from the transmitting station. They eventually become so weak they cannot be detected. Between that point and the place where the skywaves reach the Earth, it is often called the dead zone, where the station's signals cannot be heard. This dead area is called the skip distance. The ionosphere is closest to the Earth at noon and causes the sky waves to return to the Earth at a point closer to the transmitting station than they do at night. Radio stations can send farther at night than they can in the daytime because the ionosphere is higher and the station's sky wave rate returns to the Earth at a point which is further from the station than it is in the daylight.